Okay, so welcome back. So we shall be continuing with our discussions on the compact AES SBox implementation in polynomial basis. So we were talking in the last class on the squaring and scaling operations. So we will be continuing with that and try to see how we can eventually get the overall SBox design. So in order to start with, right, we have already seen that how we can decompose a GF2 power of 8 circuit into GF2 power of 4 operations. So let us try to now take a look about how we can implement a GF2 power of 4 inversion, which you remember was one of the components in my circuit. So therefore now again in a similar fashion, the inverse I can again write a GF2 power of 4 element equivalently in the field GF2 power of 2 whole power of 2. And therefore, right, the components say delta, right, will be equal to, suppose delta is the inverse of gamma 1 z plus gamma 0 whole to the power of minus 1, and the result is say delta 1 z plus delta 0. Remember that when you are doing this, you are doing a modulo with z square plus z plus n. Okay. So therefore, the results here are exactly like what we have calculated previously, and therefore the circuit also is exactly similar. Okay, expressed that now, except that now these elements are in GF2 power of 2. Okay. So therefore, right, if you want to realize this, then we have got GF2 power of 2 multipliers, and the inversion is also in GF2 power of 2. Okay. So therefore, right, again, so therefore you are now doing operations in GF2 power of 2, but if you want to, when you are doing operations in GF2 power of 2, you can again, like decompose the elements, say you can write when you are multiplying say 2 elements, say like when you are multiplying 2 elements like gamma and delta, say gamma is G1W plus G0. So now again I am breaking GF2 power of 2 as GF2 whole power of 2. So I am writing this as, so remember that G1 is 1 bit and so GF2 power of 2 I am writing as G1W plus G0, which means G1 is 1 bit and G0 is also 1 bit. They are both elements from GF2. Okay. Likewise, delta is D1W plus D0, which means D1 and D0 are in GF2. So when I am multiplying gamma and delta, that means G1W plus G0 with D1W plus D0, again remember that I will get a term like W squared. So I have to again have an irreducible polynomial. The irreducible polynomial in this case is W squared plus W plus 1. There is only one irreducible polynomial choice. Okay. So that is why, right, but again like this equation can have 2 roots, and therefore you have got 2 polynomial basis choices. Okay. Suppose I take one of them and let us call it as W, and therefore, right, I can write now this as W into as follows. So this is my simplified expression. Note that if I do that in this fashion, I will have 4 independent multiplications which I have colored as in the color red. You can also write that in an equivalent form as shown here, but note now you have got to do 3 multiplications. Okay, like here is one multiplication, here is second one, here is another multiplication, albeit at the cost of doing few more XORs. Okay. So note the compact expression. So therefore this is apparently a compact way of writing it, and but now interestingly note that the multiplications and the additions are now in GF2, which means now they are 1 bit elements, and therefore they are nothing but AND gates and OR gates. Okay. So finally, right, we have gone down to bits, right, essentially, and we essentially do not need to decompose any further. Okay. So now once you have done an operation in GF2 power of 2, that means you know how to do a multiplication in GF2 power of 2. Let us get back to our squaring and scaling, okay, and see like what is the effect back. Okay. So this is a very interesting thing. For example, you can see that a scaling operation to compute, so let us just compute as first of all a simple scaling with n and with n, where like one of them is say n equal to W or say n equal to W square. Okay. So remember that we had such kind of operations in our circuit. For example, if you go back, right, here is a scaling operation where you are doing with n. Okay. So therefore it is important to know how to do that operation, and it's quite simple. So what you can do is that, so now you have got elements as G1W plus G0, that is an element in GF2 power of 2. You are multiplying that with n equal to W, and therefore when you multiply this, you will get omega squared G1 plus G0. Remember that omega squared again you can decompose like what we have seen before, because you know that omega square equal to W, or omega square or W squared is equal to W plus 1, and therefore with that substitution you will get W into G1 plus G0 plus G1. Okay. Likewise, a scaling with W squared can also be represented in this fashion. We have got G0W plus G0 plus G1. Okay. So, now when you are doing a squaring and scaling, that means why do we like, now let us try to understand the importance of this circuit, why we are doing squaring and then scaling, why we are trying to combine these two circuits. Okay. It turns out that in GF2 power of 2 this operation is free. Okay. For example, what I am doing is that I am trying to do W into tau square. Okay. So, suppose n equal to W and I am doing W into tau square, then the operation that I am doing is W multiplied with G1W plus G0 whole square. And this, right, is nothing but G1W plus G0 plus G1. Okay. So, again I have substituted W square as W plus 1 and this is what I get. So, now if I again like multiply with W, I get W square, and then again I replace W square with W plus 1, and finally, right, after few simplifications I get G0W plus G1. So, you note that my input was G1W plus G0. After doing squaring and scaling, I just get the same result, only swapped. So, I just need to swap the higher the higher part with the lower part. Okay. So, therefore, this result, this is the 2-bit result, these are 2-bit value because G1 is from GF2, G0 is also from GF2, and the result, right, of squaring and scaling is nothing but a swap of these bits. Okay. So, this is important to note that we see that squaring and scaling operation is free in the polynomial basis of GF2 power of 2. Okay. So, therefore, right, this also has an effect on the bigger or like the top, the squaring and the scaling in GF2 power of 4. Okay. So, if you remember, right, we stopped at this result where mu gamma square was equal to z into n tau 1 square plus n square tau 0 square plus tau 1 square. Okay. So, now if you want to take the advantage of the previous result, that is the squaring and scaling is free in GF2 power of 2, you can actually write this n gamma 1 square. So, remember that this is an operation in GF2 power of 2 and now this is free. So, you suddenly observe that this operation is free, and you can also write this operation as n multiplied with n gamma squared. So, again if you do that, right, you just need to do one scaling operation because the part in the parenthesis is free. Likewise, gamma 1 squared you can actually write as n squared into n gamma 1 squared because n to the power of 3 is 1 in GF2 power of 2, okay, because there are 4 elements as I said, and therefore, right, you essentially again have this free and you just need to do a scaling with n square. Okay, and we have already discussed about the corresponding equations on how you can do scaling with both n equal to W and with n equal to W square, that means n and n square. So, if you just plug in these equations, you should be able to perform these two scaling operations, that means scaling with n and scaling with n square. So, therefore, the entire operation can now be done with one addition and with two scaling operations which we have already seen. Okay. So, finally, right, you have one more step to be observed, which is like the inversion in GF2 power of 2. Like before, we can again obtain the inversion in a similar fashion. Therefore, if you take an element G1W plus G0, which is an element on GF2 power of 2, and if you want to calculate capital D, which is the inverse of G, then D is equal to D1W plus D0, okay, which is the inverse of G, which is G1W plus G0. So, therefore, again when you are doing these operations, remember that your irreducible polynomial will be the irreducible polynomial of this decomposition, which is W squared plus W plus 1. So, you are basically writing your GF2 power of 2 element now in terms of GF2 elements, okay, and the corresponding irreducible polynomial is W squared plus W plus 1. So, therefore, right, if I again apply the equations which we have seen in the previous case, and just because essentially nothing changes except the variable names. So, if you just use the same equations, you get D0 which is equal to G0 plus G1 into G0 squared plus G0 G1 plus G1 squared whole to the power of minus 1. Okay. But note that this element is now a GF2 element, okay, and in GF2, which means either it is 0 or 1, the inverse of 1 is 1 and the inverse of 0 we define as 0. Okay. So, with that definition, I can actually replace or just neglect this minus 1 or neglect this to the power of minus 1 and rather calculate this as G0 plus G1 into G0 plus G0 G1 plus G1, okay, and this turns out to be G0 plus G1. So, what we are trying to say here is that for any non-zero GF2 element, that means suppose it is 1, then I can write G squared as G, okay, and likewise I can also write G to the power of minus 1 as G. Okay. So, therefore, with this simple observations, right, I get D0 as G0 plus G1, and likewise my D1 is also equal to G1 into G0 plus G0 G1 plus G1 to the power of minus 1, but I can neglect that minus 1 in a similar way, and therefore I get only G1. Okay. So, if you observe like G1 into G0 plus G1 square G0, so that G1 square will become G1. So, I will get G1 G0 plus G1 G0. Remember, these are all additions in GF2 field. So, therefore, it is an XOR. So, therefore, these two will cancel. So, I will have got G1 square which is equal to G1. Okay. So, note the special case of the inverse of 0 is handled by these equations implicitly, because if my input is 0, my output is 0. Okay. Like if I plug in an input say D1W plus D0 and I want to calculate the, if I want to calculate say the inverse of G1W plus G0, where both G0 and G1 are 0. Okay. So, if you plug into these equations, your D1 will be equal to G1 which is 0, and D0 is equal to G0 plus G1. Since both of them are 0, you still get 0. Okay. So, therefore, these equations implicitly tackles your special case of 0 inverse being 0. Okay. For other cases also it correctly calculates. So, therefore, right, finally, we have kind of understood the underlying field operations. Now, we need to put them together. Okay. So, remember that what we will be doing is we will be first of all realizing the topmost circuit in GF2 power of 8, and then all the underlying operations we will be essentially doing by the equations that we have studied till now. One thing we need to still discuss is about the field isomorphism between GF2 power of 8 to GF2 power of 2 power of 2. Okay. Of course, we have seen few techniques in the previous class. In Kandide's paper, there was a very nice technique which we can also adopt here. So, what we can do is that we can rather take an element G, which is say an element in GF2 power of 8, which is a standard representation of an element of the state matrix of AES, and it is denoted by the byte G7 to G0. Okay. Now, the polynomial representation for this element in GF2 power of 8 is therefore G7 x to the power of 7 plus so on till G0. So, note that all these elements like G7, G6 and so on till G0 are all elements in GF2, that means they are either 0 or 1. So, if you want to map this element to a new element in a new basis, so this again will be having 8 bits in the vector, because the mapping has to be 1 to 1, so it has to be equinumerous. So, again I will get B0 to B7, but interestingly we need to understand the transformation of the transformation function from B0 to B7 in terms of G1 to G7 and vice versa. So, in polynomial basis, therefore, right, when you are expressing like GF2 power of 8 in GF2 power of 4 squared, so I consider this quotient field. So, therefore, right, in this quotient field what I am trying to do is that I am trying to basically simply write G as gamma 1y plus gamma 0, where each of these gamma 1 and gamma 0 are elements in GF2 power of 4, but again that is also written as GF2 power of 2 whole power of 2. Okay. So, therefore, we are trying to do this in a recursive fashion. Therefore, each of these gamma can also be in turn expressed as capital gamma 1 z plus capital gamma 0. Okay. So, to summarize, what I am trying to say is that you are trying to express this polynomial polynomial representation in GF2 power of 8 in terms as like G being equal to gamma 1y plus gamma 0, where each of these gamma 1 can be, or each of these gammas, right, like gamma 1 and gamma 0 can be expressed as like capital gamma 1 z plus capital gamma 0. Okay. So, likewise, right, remember that these are now element in GF2 power of 2. Okay. So, therefore, you can further write it as B1W plus B0, where each of these B1 and B0 are elements in GF2, and therefore, they are nothing but bits, single bits. Okay. So, therefore, equivalently you can write this polynomial as two parts. The first part is this, where the where the indeterminate is y, and the lower part is the constant. Okay. Again, the lower part you can decompose into two parts. The first part again will have z as an indeterminate, and the lower part will be constant. Okay. So, therefore, it will be something like B3W plus B2 into z plus B1W plus B0. Likewise, the top part, that is the like B7 to B4, you can arrange that as B7W plus B6 z. So, this is the independent is z, and the corresponding constant term is B5W plus B4. Okay. So, therefore, if you now kind of like sort of simplify this and elaborate this, you will have B7 the B7 will be like multiply with w, z and y. So, you will get w, z, y here. Likewise, for B6 you will get z multiply with y. So, it is z, y here, and for B5 you will get w with y. So, you will get w, y here, and with B4 you will get only y. What about the lower parts? So, B3 will have a term w, okay, and w, z. So, you will get w multiplied with z. For example, for B2 you will have only z, for B1 you will have w, and B0 it is a constant term. So, therefore, right, the mappings you can actually elaborate them in the form of a matrix. So, what I mean is that if you want to convert say G7 to and you want to get like the corresponding elements, or you want to get the corresponding mappings, then you need to know these values. You need to know the values of say w, z, y, and so on. Okay. So, how do you get these values? So, as I said that we start the like the mapping is decided for a choice of the basis, which is denoted as y, z, w. So, remember that y is my polynomial basis for GF2 power of 4 square, and z is my polynomial basis for when GF2 power of 2, and w is my polynomial basis when I am expressing in terms of GF2. Okay. So, these values are fixed by the choice of the parameters mu and n. Okay. And as we have discussed, right, mu needs to satisfy some criteria, n needs to satisfy some criteria. So, here are some choices which was proposed in Can-Wright's paper. So, remember that I can also express them as a GF2 power of 8 element. So, therefore, I express mu as in a hexadecimal notation, I express that as EC, n I express as a BC. Okay. And if you use this and solve the first, suppose I take this value of mu, then I get my equation, or the topmost polynomial becomes y squared plus y plus mu, and therefore, if you solve it, right, you should get a value of y which is say 0x ff. Okay. Likewise, for z squared plus z plus n, if you solve, you will get 5c as a value for z, and likewise if you solve w squared plus w plus 1, one of the choices is BD. Okay. For other choices, you will have other circuits. Let me as an example explain the choice of n, like as I said that suppose n is equal to 0x BC. So, if you want to write BC, you can express BC as 1011, that is your elaboration for B in binary, and likewise D is nothing but 1100. So, therefore, right, this polynomial, if you want to express this as a GF2 power of 8 polynomial, this is nothing but x to the power of 7 plus x to the power of 5 plus x to the power of 4 plus x to the power of 3 plus x squared. Okay. So, remember the choice of n has to be such that it has to be a root of the irreducible polynomial of GF2 power of 2. That is why how we were essentially choosing n, right. N has to be a root of the irreducible polynomial of GF2 power of 2, and the corresponding polynomial was w square plus w plus 1. Therefore, n has to be a root of w square plus w plus 1. So, let us verify this, and when you do this, right, we will always be performing modulo with the AES polynomial, which is x to the power of 8 plus x to the power of 4 plus x cube plus x plus 1. Okay. So, here is a simple verification of that. I take n square. So, n square, right, is nothing but the square of n. So, this is my n. So, if I square it, everything will get powers of 2, okay, because again I am doing a characteristic 2 operation. So, I will get x to the power of 14 plus x to the power of 10 plus x to the power of 8 plus x to the power of 6 plus x to the power of 4. So, note that n plus 1 is nothing but x to the power of 7 plus x to the power of 5 plus x to the power of 4 plus x to the power of 3 plus x squared plus 1. Okay. So, if I use this AES irreducible polynomial as my reduction polynomial, thus if you substitute x to the power of 8 as x to the power of 4 plus x to the power of 3 plus x plus 1, and if I multiply x on both sides, I get x to the power of 9 as x to the power of 5 plus x to the power of 4 plus x squared plus x, and again if I multiply x, therefore, I get x to the power of 10 as x to the power of 6 plus x to the power of 5 plus x cube plus x squared. And now, if I want to calculate x to the power of 14, right, I can multiply x to the power of 10. Okay. So, therefore, this is my I essentially want to calculate say x to the power of 14, and x to the power of 14 essentially turns out to be x to the power of 10 plus x to the power of 9 plus x to the power of 7 plus x to the power of 6. Okay. So, note that when you are doing these operations, right, I am always doing I am reducing via this polynomial. Okay. So, this is my irreducible polynomial which I am using to like take modulo operations. So, therefore, now when I want to sort of like reduce x to the power of 10, Therefore, I will plug in this elaboration of x to the power of 10, that is x to the power of 6 plus x to the power of 5 plus x to the power of 3 plus x square. X to the power of 9 is x to the power of 5 plus x to the power of 4 plus x square plus x, and this is what I plug in here, and I have of course got x to the power of 7 plus x to the power of 6. If I simplify this, this turns out to be x to the power of 7 plus x to the power of 4 plus x cube plus x. If I just go ahead and calculate n square plus n plus 1, of course I have to do few ugly operations here, but interestingly, right, if you elaborate this, then all these terms will get cancelled out, and finally you will get 0 to prove that indeed n square plus n plus 1 is 0, which means that like that n is a correct choice. Okay, the n that we have chosen is correct. So likewise, one can check the other constants and the bias values too. Okay. So therefore, the final step is this, that now once you have this G7, you have got these values, right, as we have seen. So we need to calculate these values like WZY, ZY and so on, and each of them will give you individual columns of your matrix. So you see, you have got 8 components here. Say for example, WZY will have a corresponding value, and so on. Everything will have you can calculate these individual values, and if you calculate them right, then each of these columns will stand for the corresponding values. Okay. For example, this one will stand for say WZY and so on. Okay. You can observe that the last column is 1, and that also you can verify here that like in your elaboration the last column is nothing but 1. So therefore, like B0 is multiplied with 1, and therefore your last column of this matrix is 1. That means 1 gets mapped into 1. So this mapping is denoted as X in the form of the field. This is the mapping from GF. Like because you have got this as an input and you are calculating this as an output. So remember that this is an element in GF2 power of 8. So you are basically translating GF2 power of 2 power of 2. Okay, GF2 power of 2 whole power of 2 whole power of 2 to GF2 power of 8. Okay, and the inverse mapping of X, that is X inverse, can help you to translate from GF2 power of 8 to this composite field. Okay. So finally, right, what we have seen is essentially also elaborate and taken from, you can refer to this textbook for more details on how these implementations work. And essentially, right, to conclude, what we have discussed is, we have discussed about how to compute the S box output for a given byte. We apply for that the inverse transformation, which is x to the power of minus 1, and this transformed element is therefore in the composite field, which is GF2 power of 2 whole power of 2 whole power of 2, and the discussed circuitry is then used to get the inverse in composite fields. And finally, the transformation, that is X, I mean the transformation X is applied on the result to get the result back in GF2 power of 8. So one can either separately apply then your affine mapping, or you can try to combine the affine matrix with the matrix X. Remember that in affine mapping also you have a matrix. You can try to combine that with the matrix X, but exact details of which I am not kind of formulating in my class, but I rather leave as an exercise. Okay. So let me stop here, and thank you all for your attention.